Cheers. So yeah, I'm a software engineer in the blockchain space now, so got a pretty good understanding of peer-to-peer heuristics in general and mechanics. So the talk is, a reference to at least the title is a reference to smashing the stack for non-profit. I like that article. So let's just get into the talk. The thing's gone off, by the way. The thing here.
The display on the screen?
Yeah.
You got it on there?
No. That's all right. I mean, I can. Let me see something online.
Are you on mute or extended?
Yeah, extended. Let me just bring this down here. I'll be able to see. Great. Okay, fine. Cool. Thanks.
Sure.
Yeah, it's fine. Cool. Cheers. So, yeah. So the there we go. Yeah. So there's two main kinds of exploit classes. So the first class is logic exploits. So I don't know, you have like some buffer overflow because you didn't keep track of your integers correctly. You have I don't know, some if statement that's wrong somewhere or whatever. That's quite easy to fix generally. It just takes a patch, and those exploits affect single clients, whereas the other type of exploit, which is flaws in the design, so that's architectural flaws in protocol, architectural flaws in how your database, I don't know, gets data from your disk or whatever. Those are far harder to fix because they require meta heuristics. These in peer-to-peer protocols, especially, or generally any kind of networking protocol where two clients must agree on a way to exchange information, those are even harder to fix because you can't just fix your own client, because then you won't be able to talk to the rest of the network. So you have some so you have a synopsis of logic exploits there. All right. Anyways, and then a synopsis of design exploits there. So you can see design exploits. I just think that I've said you can't fix them unless the entire network upgrades, especially for peer-to-peer protocols. So peer-to-peer networks. Yeah, peer-to-peer networks are very prone to design. Oh, God damn it. Yeah, this is annoying. Anyway. So peer-to-peer networks are very prone to design class exploits. The peer exchange and discovery mechanisms contain subtle emergent properties that are easily abused. And you can't change the peer exchange or discovery mechanism without breaking compatibility. So in the BitTorrent protocol, which is what we're going to be looking over today, is the peer exchange mechanism is DHT, distributed hash table, which is based on Kademlia. So there's a synopsis of that there. Great. So it's the world's largest P2P network in terms of usage and traffic, I think. BitTorrent traffic accounts for something like 30 to 50% of the world's bandwidth-intensive traffic at certain times of the day. I think Netflix is like the second largest bandwidth user. The spec of the BitTorrent protocol kind of evolved over time without any real oversight or guidelines. There's like the Bitcoin enhancement proposals, which sort of are like community voted on. But if you tried your hand at implementing a BitTorrent client anytime in the last like 10 years, it's quite hard. So most of what people have done, they've taken the reference client or whatever open source client, and they've implemented that, and without really understanding the effect of what certain protocol decisions mean, and so there's the worst mistakes in the reference client. They get ported into everything else. Let's see, torrent. Yeah. So in terms of the DHT. Right. So, oh, is it going forward? All right. So the BitTorrent enhancement proposal, number 5, came out in 2008. So that's what introduced the DHT. So if you have, you probably use magnet links nowadays. So that's what allows magnet link to work. The magnet link has a part of the protocol. A part of the link is the first part of the magnet link is called the BitTorrent info hash, and then the rest you have sort of announced service. So if you go to, I don't know, download your Debian ISO, because that's what everybody does with torrents, you'll generally see a link which has a bunch of garbage at the beginning. So that's a SHA-1 hash. It's a SHA-1 hash of the metadata and the torrent. It's a SHA-1 hash of the metadata and sort of the torrent Merkle tree, which is like a tree of hashes of the file. And then you have the other part, which is the announce list. The announce list is what keeps track of the trackers. So I don't know, router.bittorrent.com is BitTorrent.com is a tracker. That's what in the old days you would only be able to rely on. That's what keeps track of the torrents. You register a torrent with the tracker, it keeps it in its list. You can create torrents from the tracker. So it's a central server that acts as a mediator. But you can actually, with magnet links now, you can take away that central server completely, because it uses the distributed hash table as sort of like a distributed key value store to do natural traversal peer exchange. And they've added on top of this, they've added another protocol extension, which is BEP0009, which allows you to use the torrent in band to get metadata about the torrent, given just a SHA-1 hash of the torrent file. So that's why nowadays you can, if it's whatever, the Pirate or something goes down, it's very easy to get it back up or click on the side, because all you have to do is just keep a list of the info hashes, and you can always find other peers through the HT. What's the torrent? Let's see. Okay. So yeah, in its basic form, torrent's just a hash. The info hash is just the torrent metadata, like as I said, and it's how peers are found for a particular torrent. So there's a sort of like a dump of like a general torrent file for you went to ISO, and you can see that there is some. That's so annoying. You can see that there's, there's comments, there's some random fields that don't really matter. There's the announce field, which is what has the trackers, in a regular torrent. There's the info hash, which is what I described. The file length, the number of pieces, and the total length have the Merkle tree. So the Merkle tree is like a tree of hashes. It's one of the ways that the BitTorrent keeps track of pieces that you've downloaded, and it's also keeps track of how it's an easy way to verify that someone hasn't given you the wrong data for a certain piece. So if if I'm downloading like an ISO, it's important that that doesn't get corrupted, but more so that that doesn't get maliciously altered. Maybe I'll one of the chunks in the ISO is the SSH binary, and I'll backdoor it or something. So the way that this is prevented is you take a hash of the entire file, and then you split actually no, never mind. So you're getting confused with the other type of filter structure. So yeah, you split the entire file into chunks, which is like, I don't know, a 1 kilobyte chunk, and so you hash each of these chunks, and then so that's like that's layer 0, say, of the tree, and then you take each pair of hashes and you hash that, and you hash both of the hashes. You can concatenate them and the hash, and so then that forms like level 1, and so level 1 the level 1 hash has 2 nodes for that point to the lower hashes, and then you do this until you only left with 1 root node, which is the Merkle root, and So if I request a block from you as a peer that I want to download from you, I don't have to wait until I've downloaded the entire torrent to know that I've downloaded the right block. Plus, I don't have to hash the entire 10 gigabyte torrent just to make sure that you didn't give me the false block. So it's good for error correction, but it's also good for data integrity. Make sure that you don't. So make sure that people don't get exploited. So a DHT node, distributed hash table node, what is it? In essence, each peer that participates in the DHT is a DHT node, and each peer maintains a list of peers, which is the DHT routing table. So the DHT node has an ID, which is also a SHA-1 value, so like a 190-bit, well, to the 190 value. And there's a few different protocol messages, but the most important one for sort of in relation to torrents is the get peers message. So these messages are like B encoded, so which is like some weird binary encoding that the BitTorrent protocol uses. It's just like, it's kind of like ASN1 or RLP. So the way that the DHT works and the way that Kademli works, the way that almost all distributed DHTs work, almost all DHTs work is they use something called sloppy distributed hashing. The concept of sloppy distributed hashing is you have the content is hashed, and that's how you refer to, that's how you ask for content. You have a hash. And you also have an ID, which is your personal sort of identity in the network. And you don't really look at IP addresses or anything like that in terms of fetching and identity management. And what you do is, if you are being introduced and keeping your routing table in the network, you always try to find you try to keep your routing table, the peers of your routing table you try to keep IDs that are closest to your own ID. And because it's a SHA-1 hash, it should be technically equally distributed. So if you have a high entropy input of the SHA-1 hash, which creates your BitTorrent ID, then this sort of, in theory, can cause equal distribution in the links between the nodes, right? So in the sense that if I generate a random value and I hash it, my hash result is going to be all over the place. So if I always find peers that are close to me in the hash, those peers are going to be globally distributed. Hence, we have sort of good network connectivity in terms of variety and distribution. And this is this is kind of like the Hamming distance in terms of the closeness to your node to another node is like the Hamming distance, meaning like how many bits are different in your ID compared to the ID of this node that you've been introduced to. And nodes that are very far from you, don't care about them too much. You always keep a huge, but the nodes that are closer to you, you have a very dense routing table. And so this means this has implications for finding files, because again, files are as well categorized by SHA-1 IDs. So I take a file, I take an info hash, which is a SHA-1 hash, and I want the Ubuntu ISO. The way that the heuristics of the BitTorrent protocol find this file is I will look at my routing table, and I have some peers. So say that this hash is very far away from my own node ID. So I look at my routing table, and I have a lot of peers close to me in terms of in the ID hash, and a few other peers sparsed out. I'll take the peer with the node ID that's closest to the info hash of the torrent that I want, and I'll ask them for the peers. I'll ask them, do you have any peers that are announcing that they have this info hash that they can contribute to me? And so the node you queried will look into its routing table, and we'll see, okay, no, probably I don't, because you probably won't get in the first hop. I don't have peers that have announced this hash, but I do have peers closer to this hash than you, because I'm closer to that hash. And so it'll return a list of those peers that are closer. Then I do that same step again with the peers that it's returned to me, and whatever, and so on. After like so many hops and so many iterations of this protocol, you will get connected to a peer that is very close to the info hash, the peer ID, with a peer ID that is very close to the info hash of your file. And then that's where a lot of, that peer, the sort of the bucket of peers with the peer IDs closer to the info hash kind of act as the backbone router for that info hash. They get most of their connections are routed through them. So that's in a quick summary how sort of you find files through the BitTorrent networks when you're using DHT. When you're using a tracker, the tracker just sends you peers because it keeps a table, kind of. It's a little different in that. So the BP0005 supports the following routing peer messages. So you have the ping, which just makes sure that the nodes are alive. So you want to prune nodes in your routing table that, obviously are dying and they don't reply to you. So a lot of nodes can't reply to you, can't be reached. They can only reply to certain messages, like if they're behind NATs or something. Find node, finds a node given a node ID, which is like sort of the equivalent of get peers without the announce. I just want to find this specific node because maybe I want to, if I want to get connected to the network on the first iteration, I'll just generate like 10 random hashes, and I'll ask my Bootstrap node, just find me 10 peers that are like equally distributed, and I'll start building my routing table. One important concept here is if you have just a magnet link info with just a info hash, so it's literally you just have a hash of the torrent that you want to find. And you have no tracker, you haven't connected to anybody, you have no peers yet. So how do you connect it in the first place? Obviously, you need somebody to be aware. At least if you're doing NAT reversal, you need somebody to be aware of you before you can do the exchange. So there's a few things called like supernodes or bootstrap nodes in the DHT. You can run your own bootstrap node if you want, and there's just daemons around. So the biggest bootstrap node is run by like BitTorrent.com, and so if you hit port 6881 on router.bittorrent.com, that's a bootstrap node, which will bootstrap your routing table. It doesn't give you files. It doesn't do anything other than keep a very sparse, equally distributed routing table and reply and sort of act as intermediary for people who want to bootstrap. And again, get peers is whatever's explained. Create a routing table for the nodes closest to the info hash ID. So that's like the basic idea behind sloppy distributed hashing. And the announce peer, which signals to the nodes, to basically all querying nodes or all your routing table nodes, depends on who you're responding to, that you control this node, and like you are providing this file or looking for this file, or you leech. Even if you're a leecher, you can provide data. So as long as you have data, you're kind of a provider anyway. Yep. So and then there's some like sanity checks such as if you can't announce peer, you can't sort of send an announce peer message just to random people in the network, because otherwise then I could subscribe you to a torrent that you didn't sign up for, then I could just DDoS you. So there's like you concatenate the IP address with some random numbers, and that's a token. So when a node asks you for peers and you reply with an announce peer, you must reply with that token. So you don't subscribe people to random messages. But this only prevents content sort of injection into other people. This doesn't prevent people getting injected the wrong round tables, which is what we'll cover in a bit. Okay, let's go down. Right. So the properties of the DHT are such that you can build a serverless torrent engine. So there are a few of these around. They're not really known or popular because there's, I don't know, the Pirate Bay or whatever people use now. So, if you want like your random torrent about random things, you will go on one of these centralized sites. But you can easily build your own sort of local torrent search engine by scraping the DHT. So these are called DHT crawlers or DHT spiders, whatever. So yeah, all you're doing is running a daemon, which is a DHT bootstrap node, and people, you just keep like a healthy, in the standard BitTorrent protocol, you're only allowed to keep up to 8 nodes per bucket, and you should not keep more than like K buckets, and you prune connections out, and so this guarantees that the network is healthy in terms of like topology. The topology between nodes and the routing tables stays randomized, and so you don't have like aggregations of nodes that connect to each other, but then they're not connected, so you don't have splits in the network, basically. But if you're just running a crawler, you don't have to listen to that. So you can take your huge routing table and just like store it forever and listen to all the peers. And anytime you get a get peers, so like when you're listening to get peers, somebody is asking you, do you have any peers that have this info hash? And when you get that get peers, you basically, it's basically a message that says this IP address or this set of nodes is looking for this file. You can reply, if you fake reply that you have all the info hashes, you'll eventually get connected to pretty much every single node in the network in terms of, like, you'll be in the routing table of pretty much all nodes. Especially if you run like 10K different nodes, you can use one IP address, but you can run like 10,000 different IDs on your one IP address. And so in, I don't know, 2 to the 10th steps in your SHA-1 hash space. And basically in this way, you can kind of be guaranteed to be in almost the entire network's routing table. And so this is also what, those copyright companies do. They run these kinds of nodes, and they don't have to see you download something. They don't have to give you the file. All they do is listen for get peers request, and they're like, this IP wanted this info hash, so clearly they're trying to download this torrent, or they're seeding this torrent, and that's why it's really easy to do like mass automation of these, like the letters you get if you downloaded the wrong thing, or if you run a server and somebody's run a torrent on your server, because it's not very resource intensive to just keep track of the entire BitTorrent network, at least not the info hashes part, and again, there's another thing called BEP009. So say like I'm running this sort of crawler node, and someone does a request a get peers for me, and requests this info hash. Even if I don't know what that info hash, even if I don't know what info hash that torrent specifies, I can in my other node issue a like get metadata base. It's basically a get metadata command for this info hash, and the network will provide me the file name, the Merkle tree, and whatever of this torrent. So I get I get the name of the torrent. So that's how you build a search engine. You can resolve info hashes to. It's kind of like a domain name resolution system, but like for torrents. Instead of domain names, it's like torrent name server system. And so yeah, that's how it's so easy to get like those thousands of letters. They just have automated bots that just spam these out to like the autonomous system zone owner, like Amazon. They're like, these IPs download these things, even though you don't really have proof. You could also be running a DHT torrent crawler, and then a lot of people are like, okay, they get scared and they just comply. But that's one really cool thing about the DHT and the current BitTorrent network that people don't realize, is that you can all run your own Pirate Bays with like, I don't know, 1,000 lines of code. That's what this site called BTDig does. There's like plenty of sites run by people who just have fun with it. And it's cool also as sort of network investigation, because it's, you can sort of sweep through the entire BitTorrent network and see like the topology of the BitTorrent network evolve over time, which gives you like a clear view of the network than of a network that size that you usually wouldn't see unless you're like running a router background or something. Right, so yeah, there's these, I just talked about this, they're crawler spiders and decentralized network, blah, blah, blah. So you can without ever uploading a single torrent. So yeah, I mean, one of the disadvantages of the DHT as opposed to, it's like setting up a site like the Pirate Bay, is that if there is nobody serving that info hash at a certain point in time, you cannot get information about that torrent. Whereas, like, for example, on the Pirate Bay, all I have to do is do a keyword search, Mr. Robot, okay, there we go. Or I can look up an info hash and they're like, okay, I get the resolution. Whereas, obviously, it's a real-time availability network. So if nobody is providing an info hash right now, you can't figure anything out about it. But chances are that if you stay on long enough, you'll find it eventually. There are some like propagation delay things that could make it difficult, but generally you can build up a pretty good database. It takes like I think if you run optimized code, maybe takes like 1 day, like 30 hours to basically duplicate the entire TPP database locally, which is not bad. And it's not because it's bandwidth intensive, it's because it's the propagation delays. Okay. So the sort of the scope of this talk, now that we've gotten all through all the prerequisites, you can piggyback onto the BitTorrent DHT and use it to aid NAT traversal, or act as a command and control server. So NAT traversal, if you don't know, is the way that routers work right now. Is you have if you have like a consumer router and you have no ports open, and I try to, hit port like 5050 on your router, it's just going to get dropped by the router, right? Not because the router, it's not because this router is really that smart about this. It's because it hasn't seen, well, the port's not open, but it also hasn't seen a request to go out to from port 5050 to whatever port. And if you take the UDP example for NAT traversal, and this is how sort of peers connect to each other behind NATs, is if I, on my laptop, and I have a router here, if I craft a UDP packet that goes from port, local port, so like local port is bound port, as in the port that you receive things from, destination port is the thing that you're sending to. So if I send a packet to a host that has open ports, and so I'm sending a packet to like a DNS server, for example. So that's 53. So I'm sending, my packet is just, okay, local IP, my IP, local port, port, it's usually a random high port, so port 60,000, destination address, and destination port. So, destination address could be 8888, Google's DNS, destination port 53. When that passes through my router logs that, right? It sort of puts a check mark saying, if a packet comes back with source port 53, destination port 60,000, let that packet through. Because my router is not open to the network, so if I hadn't initiated this, so I hadn't put a hole in the router's firewall, my packets wouldn't go through. So you can do this as long as you can. You can do this even when neither of you have open ports, by just organizing yourself in another way. So if I make like just a general client that has hard-coded source port, so it's always going to come from port 60,000, and it's always going to go to port 60,000. And same to you when you want to connect to me or to random addresses, it's always going to come from port 60,000 to port 60,000 on UDP. As long as you don't have symmetric NATs, meaning as long as you don't have mobile NATs, like the NATs, the network header translators that are used in the gateways for mobile networks, because those are different. The port that you bind to locally isn't the port that gets sort of advertised once it passes the gateway, because there's like many different many different clients on the same address, so forget that one. you have to use some sort of stunt server for that. But if I'm using like a home internet line and you're using a home internet line, but both our routers, they have 0 ports open, as long as we both know each other's IP addresses, and we have this client that hard codes source and destination ports, I'll send a packet to you first, and that packet will get dropped at your router because you haven't sent anything to me yet. Now, you will send me something, we just agree on a time, you'll send me something back, and because I've sent you the packet, my route is already open. So I will get that packet even though that port is not open, and I reply to you, and it's because you have sent, you've sent that packet now, your route is also open, so now we have a open route that will sort of last, depending on like what protocol you're using or what route you're using, but it'll last between 30 and 60 seconds as long as you have some activity. As in, like, if you stop all activity, that route will sort of time out within 60 seconds, and the things will be closed again. So there, this background to net traversal, and that's a big thing in terms of like, botnets, because if you have malware, and you need to control your bots somehow, and you need some way to reach your bots, but all your bots have closed ports. So what you usually do, what is usually done, is somebody will hack like root, I don't know, like 10 random Linux servers somewhere, and it'll turn them into bot masters, right? But that's pretty fragile because you can, I don't know, the FBI or whoever is in charge of that jurisdiction can just reach out to the hosting company or just black hole those routes, and then you've lost control over your bots. Unless you have some sort of like way for the bots to like find a new bot master, but that's overcomplicated. So if you don't need that central server for to dispatch instructions to your bots, or open up routes to your bots, and the bots can just connect to each other, that's basically that's a far more resilient botnet, because you don't you can't really take it down, as in you can't just black hole every single client that is infected, right? It would be kind of hard to pinpoint at which point in the route they're infected, especially so if you have like a 1 million node botnet, and that's probably going to keep pretty healthy connections with each other bots, and they can keep routing tables and whatever. So it's pretty much, you're pretty much done. Like, it's very hard to take down a botnet like that, especially if you use piggyback onto another DHT network, which is like the BitTorrent network. The BitTorrent network has insane levels of inter-routing traffic. I mean, yeah, again, it's 40% of the internet traffic at some points in the day. On top of that, there's some interesting properties that emerge when you have such a high bandwidth network. Is that intelligent companies like the NSA do not monitor BitTorrent traffic because it's actually too much for them to log. So if you make a botnet that uses like erasure coding between torrent traffic, you're pretty much invisible to the NSA as well, which is interesting in itself and whatever. So yeah, again, because it's such a big network. Even if you have a very large botnet that shows up on radars normally, like, I don't know, the Configure botnet or the Zeus botnets, which can range from the 1 million to the tens of millions of nodes. If you have like a couple of central servers that are hitting like 10 million connections, that's pretty obvious. But if you have a distributed network that piggybacks on top of the BitTorrent, like, I don't know, there's probably like hundreds of millions of BitTorrent connections of traffic going through at any point of the day. And if you're smart about it and you like keep localized connections, route localized connections, and you sort of masquerade your bot commands as BitTorrent traffic, you can have like a botnet in the millions and never get detected. Well, I mean, it's very hard for it to get detected because it'll just look like BitTorrent traffic, especially because a lot of BitTorrent traffic is encrypted in some weird way, which is not very secure, but it makes like stateful packet analysis very hard, especially at those scales. So yeah, and then as well, the DHT is so large that it's generally pretty well connected. So even if your network is, so the larger your network is, the larger your subset of the network is, as in your botnet within the DHT, the less the propagation time is. But even if your network is just consists of 2 nodes, as in like me and you just want to like chat with each other using the DHT, the propagation time is only a cost at the very beginning, meaning it'll take you like 5 to 10 minutes to bootstrap to the DHT network. But once you start sort of broadcasting your get peers request, and your nodes are sort of like in the routing tables are spread across the network, at that point, when somebody new joins the network and they broadcast to get peers, that request will get to you pretty quick. So it's like a TCP connection that takes like 10 minutes to go through. But once it goes through, then you have pretty good latency. So the simplest example to exploit this DHT for your own purposes, and this doesn't have to be for malware. This can be for pretty much anything. You can build a domain name resolution system on top of DHT. You can build like a content addressing system, whatever. I mean, anything where you can have a distributed key value store that is too lenient and allows things that aren't actually torn into via key value store. So there's the steps. Generate a random info hash that is the real torrent. So just take a message like BSides, SHA1 hash that message, and then throw out a get peers request saying, I want get peers, give me peers that are looking for this hash. Eventually that info hash will get pretty well thrown out in the network. If you and your bot, client, other party, whatever server are both requesting that info hash, you'll eventually be relayed each other's IPs and also ports that you're listening on. So you'll get something like IP 127001 is listening on bound port 5050 and addressing bound port 6060. So with that information, and you'll get my address and bound port. With that information, we can do net traversal. We can do UDP net traversal, but also TCP net traversal, and micro DB or whatever. There you go. So you're done, and you're connected to each other without needing a central server for this remediation, which is it's like this Kademlia. All these DHT protocols are based off of this initial sort of design called Kademlia. So all these Kademlia-based protocols have these traits, and they've been getting a lot more popular recently. And there's I don't know if you know about IPFS, which is like doesn't stand for IP file system. It stands for interplanetary file system. So it kind of uses this Kademlia-based routing to address content on your disk. So you can publish a hash, like on some website, and as long as your node is online, people can directly take data from your like laptop's disk. And those connections are made through the DHT. Bitcoin uses a Kademlia-based routing system. It's very similar. It's not the same, but it's very similar. Pretty much all cryptocurrencies. At one point, Skype used to use a Kademlia-based routing system, but not anymore because Microsoft killed it. Like everything that Microsoft touches. But it's a lot of WebRPC sometimes uses Kademlia-based routing systems as long as it doesn't use start servers. And so there's like a trend that sort of these things are getting more popular. But at the same time, people aren't thinking about like the emergent properties of the designs in the network, because just as BitTorrent is sort of vulnerable to hijacking, where hijacking in the sense that you're using a torrent, you're using the network, but not contributing to the network's purpose, right? If I'm using the network just to resolve domain names or resolve my bots, I'm abusing the network in the sense that I'm not contributing to the network health. I'm not torrenting, I'm not seeding. Like, I'm actually damaging the network, because the way that I use my routing table to connect my bots is very different from the way that you should be using your routing table to keep a healthy DHT for torrents anyway. Okay, great. Yep. All right. So then again, the KVs, bootstrapping the network takes a very long takes a long time sometimes. Sometimes it can take a very long time depending on the network state. It's not really based on, it's not based on bandwidth, it's based on propagation speed. You can do some tricks to to like optimize this, but worst case scenario is always going to be 5 to 10 minutes. So if you have something like critical thing that like you need to know that when I make this connection, it's going to happen within like a second, it's not a good thing for that. It could take up to 5 minutes. There are many nodes that just respond to this, to every single hint of a hash, like the crawler that I mentioned before, and just debate up huge tables, and that's annoying because if you're trying to like control your bots, or if you're trying to find somebody's file on a system or DNS, whatever, you'll get a bunch of like crap replies, or like, yeah, look, I have every file you want, but then and you try to connect them and you waste time because they never connect back to you. They're just trying to crawl the network. You know, again, half of these are crawler nodes from people who just run crawlers for whatever the hell, for what reason. Companies who build up statistics, maybe some of the nodes are the NSA, I don't know. If you spend too long using the same amount of hash that nobody else uses and nobody can get a metadata torrent out of, and it's like doesn't really exist and nobody's ever seeding that torrent, it's pretty clear after a while that you're just abusing the network. But there's no heuristics in the clients to detect this. They'll just be happy with it. Like no torrent client that I know of, and no sort of no DHT do bootstrapping node that I know of keep track of this. Maybe the only exception might be like private trackers, but I don't know. I don't use that stuff because yeah, obviously like the behavior of give me all the files, but then at the same time I won't give you anything, and I'm never downloading these files is pretty obviously a crawler node, and the crawler nodes are mostly DCMA and the DMCA people, and so I guess for private trackers they might track that a lot more often or more seriously. But I mean, it's easy to track only if you're very naive in your implementation. If you are relatively intelligent in how you do it, and you pretend to be a peer, yeah, even a little bit, it's pretty hard to track you down, especially if you like fast flux your IP address in your node ID. So, on top of this, the DHT, the entire network starting tables can be slowly manipulated over time with somebody who has enough resources or the right know-how about differential changes in routing table topology depending on activity. So yeah, most clients rely heavily on the DHT IDs, which is those SHA-1 hashes that you just randomly generate instead of IP addresses. I mean, obviously, partly this is a effect of the internet because you know there could legit be many different clients behind one IP address. Like for example, a university which blocks UDP torrents, UDP ports. By the way, I had to use the TCP VPN to test my client before, so yeah, this is also how certain people can dupe trackers. Like if you ever check out the recent torrents on the top torrents on the Pirate, just if you want to see like what's popular, what people are watching. Oftentimes there's like 10 torrents by the same like random garbage name person with like more peers than are available in the entire DHT at any one time. Probably there's like Game of Thrones season 500 into the future with like 10 million peers connecting to it, and obviously it's fake. But they're inflating the numbers by just taking a few IP addresses or their botnet or whatever, spinning up like 10,000, 100, 10,000 nodes on each of these IP addresses, announcing get peer, putting out get peer and announce peer requests. And so the tracker, the BitTorrent tracker for Pirate, for example, is very naive, and it'll be like, whoa, look at these 10 million requests. Clearly, there's 10 million people seeding and wanting this file, so that shoots up to the top. I don't know why they don't fix this. It's really annoying, and it gets people like malwared often because if you don't know about these things and you're not like in the mindset of being careful, you can easily just like go, Mr. Robot, click on the first link because it's always ordered by seeders, download some malware, and then you're done. And it's like they remove these pretty quickly, as I'm seeing lately, but it's not quickly enough. I mean, because it's not like it takes a lot of time to make a new account on the Pirate. So as they remove them, like 3 more pop up, and whatever. Yeah, and you can make sure that the routing tables of each node don't overlap too much, you can actually go a long time without this being detected on a sort of I don't know, on a fraud level or an inflated level, because there's an important, let's see actually, there's an important property called equivocation of distributed networks. So equivocation means if I'm connected to you, node A, and I'm connected to you, node B, and you both send me the same request, as in I want the peers for like info hash A, I want the peers for info hash A. If I send you, both of you, two different replies, that's equivocation. I'm lying to one of you about the state of the network. Because BitTorrent clients, DHT nodes, whatever, do not track equivocation, because BitTorrent clients do not track equivocation, it's also a very hard problem to solve anyway. It requires like some sort of like graph theory algorithms and it requires like keeping like the differential states. But because they don't track equivocation, it's very easy to set up like a bunch of nodes that reply to the network. If you have enough nodes and you have them distributed enough in the network, you can reply to requests in the network in such a way that you can manipulate the routing tables of people and section off parts of the network, or make certain parts of the network too highly integrated, and just cause chaos in the network. So you could, because you can manipulate the routing tables of pretty much everybody, because none of them track equivocation. And yeah, so like one of the problems is they don't track equivocation. One of the problems is that the only health metric in the protocol specification itself is if you don't respond within 15 minutes, you're a bad node, I'll drop you. Maybe some torrent clients, from what I've seen, are starting to put in checks for if this node constantly asks for my info hash but never connects to me, never wants anything from me, and never gives me anything, I'll blacklist that node. But for all intents and purposes, once you're connected to that node, it's kind of already late. It's manipulated routing table, and that node has your IP address. So if it's like a copyright company, you're already done. Like they have your IP address, they have the intent, right? It's over. So that's a weakness in the protocol health due to too much leniency in the implementation of why nodes are good and why nodes are bad. Again, like no equivocation checks, whatever. And also emergent properties that are bad for network health in the routing table. There are some ways that like certain peer-to-peer networks, like for example Tor or I2P, which is like Tor but darknet only, they kind of get around this by being very selective with their changes to the routing table, and they will only change their routing table if they see many different validated peers also change the routing table in that way. And they have like bidirectional, like for example, I2P has bidirectional channels that are like multi-hop, so you don't know, while you don't know where the channel request came from, it's hard to abuse it in a DDoS manner because the way that those channels are constructed has to sort of follow a certain propagation format. And so if you try to abuse the network, people will just drop your requests. So the conclusion, okay, good. What? That's really, just ended the slideshow, okay. Nope, cannot see anything right now. Oh my god. Well, whatever. There you go. The conclusion is P2P networks, pretty fun. You can build services that make use of the DHT. The issues described also apply to pretty much all distributed peer-to-peer networks. Again, like Bitcoin, Tor has some of these issues. I2P, I don't know, Hyperborea. I don't know, just name a distributed network, and it's got these problems. It's hard to design protocols. There's a lot of emergent properties that you don't realize unless you do something called safe by construction protocols, which is like a game theory way of designing protocols. It's very difficult though. I mean, it requires like a lot of understanding of like mathematics and game theory and sort of logical complexity theory. So yeah, the way that the protocols are designed now is just kind of like ad hoc, but ad hoc evolving protocols will always have these issues, and because these are architectural flaws in the protocol, it's pretty much impossible to fix once your network gets big enough. There's like a good example is Bitcoin right now. There's a lot of problems with the protocol. One of them, I don't know if you follow Bitcoin at all, is like the block size and some of the equivocation issues in terms of like spoofing transactions and which block has been winning out, but it's almost impossible to change because nobody wants to change it. A lot of hardware and software assumes that the Bitcoin protocol acts this way, and to upgrade all that hardware would be insanely expensive, and so there's a lot of pressure around that. If you want, I don't know, it probably won't work here again unless you're using a VPN or something, because it seems like this Wi-Fi blocks UDP, but you can try it at home or whatever. If you take that code, compile it, it's just some C example code, and you run it in that way, and the hash is BSides or your identifier. You'll be able to do non-transversal, basically like peer discovery with anybody else who has that message. So if you had another client that you can write a Python client or something, or use Netcat and connect to those ports. Local port, actually, if you make, local port 54, destination port, whatever, and you connect to each other's IP addresses, you can directly connect with each other to Netcat. And so yeah, that's an example code. You can have fun with that proof of concept. I think it's simple enough to play around with. And then rather BitTorrent.com is the super node that BitTorrent runs. So I think that's it. We have 55 minutes. Any questions?
So I'm a malware analyst, and I find many things by moving into Git and reverse engineer who's communicating with. And I not then just pull out the hash table and find, like, the natural burst or on mass scale, find everything used.
If the person who's done this malware is naive, yes, but you can easily make some. So basically, like, you're assuming that the info hashes that these peers are using to find each other they're hard coded in the malware, right? That doesn't have to be the case. You can make an info hash that is based on, like, some sort of avenue that you control or that you can predict, but it's hard to sort of figure out from an engineering standpoint. So like the hash of some web page, or like the hash of some Wikipedia page at this moment. So I can manipulate the Wikipedia page and change that hash, right? Now, obviously, like, yeah, you can reverse the malware and connect to the network as a peer, and still build routing tables over time that will find that peer, but I don't know, traverse the entire sort of network. But it's you can have, like, segregated networks, and like my botnet is made up of 10 partitions, and each partition has its specific way of finding info hashes. If somebody like roots one of the partitions and reverse engineers it, and I figure out that they've reverse engineered it, or like I keep check on who's of the traffic of the server, or whatever, then I can just section off that partition half by half until I find the person who is manipulating the routing tables or the exploited server, whatever. There you go. Also, you can send out like protocol level equivocation messages, like on a large scale, so that, like, for any change in the routing table, for any change of peer behavior, the peer must connect to at least like 20 other validated peers with like some sort of cryptographic signature. So if you try to change the behavior of that peer, you'll immediately get found out, right? Because you're the only peer who's equivocating, or acting differently, or even if you start exploiting like 100 bots, then that's like a level of exploitation that kind of it's easier to pick up. So yeah, there's definitely like ways that you can uncover these, but there's also ways that this can be made hard. Anyone else? Did the talk make sense? Do you guys understand? Yeah. So it's pretty interesting. There's a lot of research now into safe by construction protocols, especially for things like Bitcoin. And I mean the thing that I work on for a living is Ethereum. I don't know if anybody else who's heard of Ethereum. It's more than I expected. So Ethereum is basically like Bitcoin, but instead of having just tokens, you have Turing complete, and the Turing complete virtual machine language associated to a cryptographic transaction. So I can take an address can either be an account address with value or an address that has code, and I can send an input to the address and sort of have my code run on the entire network. It's distributed in a decentralized manner. It's not really distributed, so they all validated, and so it's like serverless infrastructure, right? You can make your decentralized Google or whatever that nobody controls. But these issues are very important in networks like that because the way that like the whole is this block valid? What's the latest block in the blockchain? How can I know that I'm not being lied to about the state of the blockchain? Right now, it's only using proof of work, hash brute forcing. That's very inefficient though, especially if you want like fast propagation time or fast finalization. As in, like I send you 1 Bitcoin, I have to wait 10 minutes, more like 30 minutes a lot of the time, before I can be sure that that transaction will get reversed, right? That's shitty. Like that definitely won't work for like payment systems. So if you use something called proof of stake, which is something that instead of putting down brute forcing a hash and then making a block out of that hash, so you have that heavy blockchain computationally, you put in sort of like a deposit, as in like I bet or I back this state of the blockchain with I don't know, like 1,000 Bitcoin. And so if I am wrong, or if I manipulate the blockchain after I put in my deposit, I lose the deposit. So I'm not incentivized to I'm incentivized against lying to the equivocating, basically. But so this along with safe by construction sort of mitigation protocols, equivocation protection, it can mean that, and there's some graph theory algorithms, it can mean that given the state of a network, like the BitTorrent network, once you have a certain state of the network, once you see a sort of snapshot of the network, and you contribute to it, like you sign a transaction or something, you can estimate how long it will take to, or how many nodes need to be Byzantine meaning equivocating nodes, like malicious nodes, how many nodes need to be Byzantine before I'm at risk of this transaction being reversed. So because it's proof of stake, there's no computation time. I mean, there's no computation expensive algorithms that take like 10 minutes each. It's more about a network agreeing in a way that makes it hard for people to be malicious, because you have like a state tree of all the activity that everybody else has done in your snapshot, and so you can have like immediate finality, which is a lot cooler, and you can have like guarantees about, given my experience and my view of the network, how safe is this network, which you don't have in most peer-to-peer protocols right now. So yeah, it's a cool area of research. So yeah, if anybody else has any questions, otherwise thanks for coming.